Okay, so this is sort of a little bit of a milestone presentation here. This is actually our last presentation in which we're going to talk about enthalpy, or remember, capital H. There are a few more presentations left in this unit, but we are going to actually deviate just a little bit away from enthalpy, and we'll talk about something that's actually quite similar in terms of some of the calculations that we'll do. So anyway. Um, Last one here today on enthalpy before we kind of switch gears a little bit. So in this case, we're going to talk about enthalpy in terms of bond energy. And I say that we're headed for a breakup because when we talk about bond energy, we're talking about breaking bonds. In fact, we're also talking about making bonds. So as it says on this screen, today we will be discussing the formation and the breaking of chemical bonds and looking at the heat energy involved in each of these processes. So you might be able to think ahead and think, well, okay, making bonds, breaking bonds, one of them is probably going to require energy, one is going to release energy, and so we will have one process that's exothermic and one process that is endothermic, and we'll actually be looking at full equations based on how many bonds are breaking, how many bonds are being formed, and then we'll be able to come up with a total delta H for the entire reaction. So again, it's everything that we've been talking about, enthalpy of reaction, but we now are going to do it a different way. So you've seen it with laboratory information. We did that yesterday. You've also seen it with basically being given information, and you're kind of working with Hess's law. So today, same deal, but now bonds. So onward we go. One term that you're going to want to be familiar with is what's called bond dissociation energy. And if you think about the word dissociation, when you think about dissolving something in a solution, like for instance, salt, when you take salt and dissolve it in water, what you're doing is dissociating the ions, the Na plus and the Cl minus. So the word dissociation means to break apart. So bond dissociation energy, the definition clearly makes sense. Energy required to break a particular bond in a molecule. This is basically how we measure strength. And we have had a discussion before about how many bonds you have and whether that makes you stronger or weaker. So if you talk about breaking the bond, obviously the more energy you're going to put in, it's going to be a way to measure strength. So we're going to see that we're going to use these measures of strength. We'll find enthalpy, and this is specifically going to be only for gas phase reactions. I don't exactly understand why it's not possible for other things, but these are always going to be gas phase reactions. So there you go. All right. So in order to move forward with this, what we need to be able to do is recognize how to draw some just basic skeleton structures. You won't have to draw full-on Lewis structures at this point, but you will need to be able to just understand the structural arrangement, the basic structural arrangement of each of these little chemicals that we're going to be working with. So in this case, what you'll see is right here I have a CH4, and hopefully by now we're clear that that's methane. And it appears, based on what I have on the product side of the reaction, that I've broken one of the hydrogens off of the methane, and now it's just the atom by itself. I know this looks funny because we have been, it's been drilled into your heads that H, hydrogen, is a Hunkelbrief and it can't exist by itself. And that's a true statement. In fact, what we're going to be calling these later are intermediate steps. This is not a final equation. This is just a step that has to happen in between. So it's okay to write it here as just the lone hydrogen atom because it's not going to be alone for very long. So we're just sort of showing the in-between steps. So when I break, because I think you would agree with me, right? I broke this bond, broke a hydrogen-carbon bond, and I have a delta H value of positive 435 kilojoules. You can see in this example that I'm doing basically the same thing, and I want to also have you note, in this case with methane, I put the H's on the end of these dashes, but in this case, I just left those H's off. So there should be an H right there, and 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 right there. This is a very common way to draw structures in organic chemistry because it's an assumption that there has to be a hydrogen attached to the carbon. So I really didn't leave this off just because I wanted to, but actually because it is acceptable notation. So what I'll have you notice on this one is, again, see the bond there, and there'd be a hydrogen. Well, here there's no dash, meaning that that carbon-hydrogen bond has again been broken, and I have that individual hydrogen atom that is now detached from the whole chemical. And I'll have you notice that the number here is 410 kilojoules. So note, in both of these examples, we've broken the same type of bond, right? A carbon-hydrogen bond. And their enthalpy values are similar. Now, are they the same? No, but they're similar. They're definitely within, not even the same ballpark, but, it's right around first base. So what that leads us to is the ability to kind of go for averages here, okay? So I just want you to have an idea that every bond is a little different for sure. However, if I had more examples of CH bonds being broken, you would see very similar values to these 430, 410, things like that. So since breaking the same type of bond in different compounds will require approximately the same energy, we can then define bond energy as an average enthalpy for breaking an AB bond, where A is atom number 1 and B is atom number 2, in any gas phase molecule. So when we are dealing with some of this, and you'll see this in the textbook, we'll use some crazy little symbols. The symbol for the bond energy of this AB bond, again, generically, they use a capital D, and I do believe that is stating dissociation. And then you have the subscript of the AB, whatever that bond might be. So if I was going to show you the bond energy for the carbon-hydrogen bond, it would say here big capital D, and this would say CH. Okay, so you can switch that up, switch the subscript up for any bond you're talking about. So real quick, pause the video if you need to, but I do need you to open up your textbooks. You're looking for page 373, and there is a big blue table at the bottom of that book, or the bottom of that page, that is for average bond association energies. So basically, you don't have to look, or you don't have to know these values. You just have to know where to look them up. And so what I'd like you to notice, as it says here in the last bullet point on the slide, notice how to read it for single bonds and for multiple bonds. So if you need to pause to get your book open, go ahead. Otherwise, I'd like to have you take a look at it with me. So first off, notice on the far left side that you have hydrogens paired with various other chemicals. Generally, we've got a lot of halogens there, the chlorines and bromines. And then beneath that, we have carbons. And notice that these are all single bonds. So let's see, the second one under carbon is a carbon-carbon single bond, and it has a bond association energy, you can see there, of 347. And then into the second column, you can see nitrogens and oxygens, and then fluorines at the bottom. You have in the next column iodines and sulfurs and silicons. And then on the far right side is where your multiple bonds reside. So if it's specifying a carbon-carbon double bond is being broken, you need to use the 614 that's listed in the far right column. And if you go down to the bottom, you'll see a carbon-nitrogen double bond. Above that, carbon-nitrogen triple bond, and you can see the carbon-carbon triple bond is actually near the top, right under the double. So just verify that you understand how to read it, and we're good to go. We know where to find our values now. Fabulous. Okay, so what you will notice is that if you compare these values, and why did I say 374? Oh, yeah. Definitely. Switch over to page 374. So on page 374, it actually offers you right in a row the carbon-carbon single, double, and then triple bond. And if you look over into the far column, you'll see the values that I have listed on the screen here. 347, 614, and then 839. And so noting here that bond energy increases as you add additional bonds. That's something we've actually been talking about before. And so if I would ask you the question here in green, obviously I have the answer available anyway, but what happens to bond length as bond energy increases. So remember that bond strength and bond energy are basically the same thing. So you recognize it as the single, the double, and the triple. I'm increasing energy as I increase bonds. And when I increase bonds, remember, I decrease length. We had talked about that before. So your triple bond is the strongest and it's also the shortest. Okay, so a little info there and kind of relating things back to where we've been before. Okay, so, sorry, almost forgot. What you'll notice here also with the kilojoules per mole, we've talked a lot about the whole like per mole reaction thing and whatnot, but this is per mole of carbon-carbon bonds. So this is assuming that you have a mole of whatever chemical you're working with, and you're going to break every single one of those carbon-carbon single bonds, and that's going to produce 347 kilojoules per mole of bonds. So if you have a lesser amount, there may be some dimensional analysis involved. If I have, say, 2 moles of carbon-carbon single bonds to break, then you must double the 347. So do keep in mind that that is pretty specific, and you may do some dimensional analysis with that. Cool. All right. Man, animations are a bit goofy today. My apologies. Okay, so using bond energy. So it says here, bond energy can be used to determine the change in enthalpy of the reaction because bonds must break for a chemical reaction to occur, right? I mean, we're not going to start off and end with the same stuff. We rearrange the atoms. So since bonds break, and we know that heat is either evolved or absorbed, we are going to be able to use that to our advantage and figure some delta H values. So we're going to do this example together, and you're going to see how it works, okay? So what I'm going to ask you to do is draw skeleton structures for the reactants that I have listed in this equation below. So you've got CH4, which is methane, which actually that skeleton structure was on the previous couple slides. And then you have chlorine gas. So if you would please take one moment, try to write the skeleton structures. Please pause the video. Okay, so hopefully your skeleton structures look like these here at the bottom. So recognizing that these are my reactants, I'm going to ask the question then, what bonds will break to form the products? So just really look at that reaction as listed up here. So I've got 4 hydrogens attached to a carbon. And here I've only got 3, and I got a Cl thrown in there. So apparently I've got to break a CH bond, right? But do I need to break the other hydrogen carbon bonds? No, because it stays together. So I am going to have to break one CH bond, a single bond that is. And then if I'm going to attach a chlorine to it, it means I'm going to have to break the chlorine-chlorine single bond to then do that rearrangement. Okay, so does that make sense? You can kind of follow it through. Okay, so these were the reactants that we drew. And we then just had a discussion on we were going to need to break one chlorine-chlorine single bond and one carbon-hydrogen single bond. And that will lead us to something that looks a little strange, okay? It's going to look like this. Okay, so notice what I did. I cleaved off a hydrogen right here from the carbon. So there's my hydrogen by himself. And then I broke that bond, so now I've got 2 chlorines by themselves. And I gave you this phrasing just a little bit ago. This is called an intermediate step. Is it the final answer? Absolutely not. These things can't survive on their own as atoms. So this is just a little in-between step as we kind of get some things rearranged, okay? It's kind of like, you have to change your clothes to go outside. But you wait until you got your clothes all the way changed before you just step outside naked. That just isn't cool. Moving on. All right. So we must take into account the amount of energy absorbed. Okay, notice my terms. Energy absorbed to break each bond for the overall enthalpy. So notice the use of symbols here at the bottom. You've got your delta H, and then I'm using that big capital D for dissociation with a subscripted CH single bond. And then I'm adding on the chlorine-chlorine single bond. Please note the positive sign. Absorbed. We're absorbing energy. Energy has to be brought into the molecule to be able to break off atoms in a bond, okay? So think about that. Think about what the word absorbed means. Is that exo or endothermic? We'll get there. Okay, next step. So we have our intermediate step. Here we are. And we need to now think about what we have to do to get to the products. And so if you can recall, we were supposed to take a chlorine and pop it over here onto the carbon, and we're taking this hydrogen and we're going to pop that in here with the other chlorine to make hydrochloric acid. So we are going to be forming a carbon-chlorine bond, and we're going to be forming a hydrogen-chlorine bond, and that will then produce this, okay? So if you would even go back to the original equation, this was what we had. We had a CH3Cl, and we had an HCl. So we've gotten our final chemicals, and those are our products. So now, this is a secondary step. We must take into account the amount of energy evolved to form each bond. And so notice here we have the same symbols with the D's and the subscripts of the little bonds, but notice the negative signs. So is that endothermic or exothermic? Okay, following? Good. All right, so if you were paying attention, you were able to devise the fact that if you break bonds, it's an endothermic process. It's a positive charge. We're absorbing energy into the chemicals. And if we're going to form bonds, that's exothermic. That's going to give off energy, and that's a negative charge. And so you can see my little bits here of my delta H with my positives and my delta H with my negatives. And now, yes, we do notice. Thank you. And now all we're going to do is basically put them together. So, yeah, and this, gosh, I said all this already. So, yeah, breaking bonds requires input of heat energy. If you need to pause it to read it all, take a minute to pause it. In fact, yeah, pause it now if you like. Read it all. We've talked about it. Okay, so now that I've got these two halves, I've got my endothermic part, which was breaking the bonds. I've got my exothermic part, which was forming the bonds. Now we're going to put it all together, and it's going to look something like this. So notice that I do have a positive, a negative for my two formed bonds. And then I can simply take a look at a chart in a book somewhere, or if it's a test, you'll be given these values right away. But the 413, and by the way, these are all kilojoules per mole of bonds. So 413, 239, 339, 427. Please do pause, verify that the numbers make sense to you, that you see where I got them from. Okay, hopefully you make sense of that. And then basically just, add it all up. And you will get negative 114 kilojoules per mole of reaction. And this negative sign, again, we've been dealing with this the whole time. It tells us that this reaction will release energy into the system. It's exothermic. Will release energy from the system into the surroundings. So it's going to give off energy. It's going to be exothermic. And that's generally considered to be a pretty stable reaction and a favorable reaction. The other thing you might note is the little approximate squiggly equal sign. And that's because when we're dealing with bond breaking and forming, as we said at the beginning, these values, the 413, the 239, the 339, and the 427, remember, these are averages. These aren't necessarily specific to the exact chemicals. So that's why it's an approximation. So this method would get us pretty close to a good value of what the enthalpy of reaction would be. However, as it says in purple at the bottom, thermochemical data, meaning that Hess's law information or actually doing the experiment, as we talked about yesterday, that's going to give you way more accuracy with your delta H. So this is a nifty little method, but it's not one that's going to get you the perfect value. So it's just another little trick up your sleeve. Okay, so if you still have your textbooks open, which hopefully you do, you'll want to take a look at page 375, and you're looking at sample exercise 8.5, and notice here I'm just saying take a look at it and be sure that you understand how the answer is achieved. So I would like you at the moment here to pause the video so that you can take some time to really look at this sample exercise and then jot down any questions that you have, and we can talk about them tomorrow. Okay, moving on. So this is going to be your example kind of on your own. I'm asking you to use bond energies to determine the enthalpy change for the combustion of ethylene. Okay, that's all I'm going to give you. Well, for now at least. What are you going to need? Hopefully somebody out there said something like, I'm going to need a chemical reaction. Yes, you're correct. Fabulous. So combustion of ethylene. Okay, ethylene. Oh, gosh. Well, maybe you remember that eth is the organic abbreviation for 2, and the ene ending actually means that there's a double bond. So that's going to actually reduce your number of hydrogens. So you may or may not be able to come up with it at this point, but combustion, that you should know. If it's a combustion reaction, I'm going to combine the ethylene with something specific, and I'm going to produce 2 very specific things because, by the way, ethylene's a hydrocarbon. So see if you can at least write out partially what I've kind of told you here, and then I'll show you the whole thing. Okay, so here's the whole thing. Your equation is this. Ethylene is C2H4, and by the way, that would be 2 carbons that are going to be double bonded together. Again, the ene ending on ethylene. And then there will be 2 hydrogens on either one of those carbons. So hopefully you can kind of picture a skeleton structure in your head. So then we have oxygen gas, which we combine it with. We have CO2 and we have H2O. Now, just as a helpful hint, if you have 1 C2H4, you should draw 1 skeleton structure. But if you have 3 O2s, you might want to draw 3 O2s. So draw the skeleton structure first. Think about what has to break and what has to form. Think about how many bonds are breaking and forming. See if you can do this, okay? Take at least a few minutes to give it a shot, and I'll show you the answer on the next slide. Okay, so I'm not sure if you were stumped or not. Obviously, I'm not sitting there with you. But if you did feel stumped, just as I go over the answers here, just really go step by step with me, okay? So I had to write this one up so you get to see my handwriting here. Okay, so you can see the reaction at the top. And what we're going to do in the first line of these yellow boxes is show you skeleton structures. So first, the C2H4, as I said, it's a double bonded carbon-carbon with 2 hydrogens on either side, and they do have a little bit of a trig planar geometry there because of space and, Vesper theory and things like that. Okay, next, O2. So does oxygen gas have a double, a single, a triple bond between the O2s, or between the 2 O's? Whew. Okay, hopefully you said double. Hopefully that's something that you're pretty good at, right away. So there's my 3 oxygen gas molecules. And then it says I have 2 CO2s, and this should be another skeleton structure that you feel incredibly comfortable with. There are double bonds between the carbons and the oxygens on both sides. So there's your 2 CO2s. And then H2O should be a no-brainer. Just make sure you put the bent geometry in there. But you have 2 H's connected to an O. So here's your skeleton structures. Now, what you need to think about here is, what do I break and what do I form? So think about this. Will I break carbons and hydrogens? Essentially what I'm asking you is, will a carbon be bonded to a hydrogen later on in the reaction? And if you look over here, no. In fact, I've got to break all of these bonds of the hydrogens and the carbons. So how many bonds is that? That's 4. Will I have any carbons double bonded together? Will that happen? Will that stay the same? No, I apparently split my carbons. So I've got to break 1 carbon-carbon double bond. Okay, you with me so far? Okay, next, will any oxygens remain double bonded together? Well, check it out. Nope. These oxygens are going to double bond to a carbon, not an oxygen. So I got to break all that. So that's 3 oxygen double bonds to break. Okay, so here's the synopsis. 4 carbon-hydrogen singles at 413 apiece, 1 carbon-carbon double at 614 apiece, and 3 oxygen-oxygen doubles at 494 apiece. Okay, follow me? Now what do we form? Well, I've got a double bond carbons and oxygens. Well, how many of those do I need? Hopefully you said 4. And then I'm also supposed to single bond oxygens and hydrogens. And how many of those do I need? Hopefully you said 4. Okay, so the synopsis. 4 carbon-oxygen doubles, 799 apiece. 4 oxygen-hydrogen singles at 467 apiece. And at that point, I've got everything broken, everything formed, and now it's a matter of just putting all those values together. And please note how I'm going to use the coefficients, okay? So the 4, the 1, the 3, and the 2 4s here, okay? Check that out. Do you see where all the numbers came from? Take a moment, pause the video if you need to, verify that you understand why I'm multiplying by which number and where it all came from. Okay, pause a second and look at it. Okay, the next thing I'm going to ask you is, do you understand why I have positives here but negatives here? Okay, take a second and think about it. Pause the video if you need to. Okay, so hopefully you were able to recognize that the 4 and the 413 are multiplied together because I'm essentially doing 4 moles of CH single bonds. And again, the 3 and the 494, 3 and 494, etc. down the line for these guys. And then remember, forming bonds is an exothermic process. It's going to release energy, and that's a negative charge. Whereas these 3 values are endothermic processes. You have to put energy into the system, and that's going to be positive values. So once you get all of that set up, you do the math, you're going to get negative 1313 kilojoules per mole. And if you run that through a significant figure bit there, you're going to go down to 3 sig figs. So negative 1310 kilojoules per mole reaction would be the final answer for this problem. Okay, so lots of thinking in terms of what you're breaking and what you're forming. Something that definitely has appeared on the AP test in the past. So something to think about, not really hard. You just have to think through all the steps and recognize you got to put all the chemicals in there, okay? So record your questions if you have them and let me know. Okay, one other thing I want to show you today. And that's going to be a graphical idea of bonding and breaking bonds. So this is bonding shown in graphical form. And what I want you to note is that on the side here, there's potential energy. You can see kilojoules per mole. So that's basically your enthalpy. So notice here a negative 432 when we form a hydrogen-hydrogen bond. And then also notice that there's another thing here listed, internuclear distance. This is bond length. So what you can see is that at its most stable position, observed bond distance, we have a bond length of about 74 picometers, which is just a really, really small measurement of meters. So this is the observed bond distance. So hydrogen-hydrogen single bond, about 74 picometers. If I begin to break that bond, you can see that the bond distance increases. So here to 150, and then finally at around 300, the atoms just separate from each other. You can also see that it's a bit higher in energy here when it's a bit too close together. So the hydrogens want to find kind of the right distance from each other. It's kind of like humans have personal space. Yeah, here the hydrogens are way too tightly packed together. They don't have their own personal space. But if you separate them just a little bit, then they can get that personal space. They feel a little bit more comfortable, and they're going to be happy there. Okay, so hopefully you kind of understand what this means. Again, if you're having issues with understanding what the graphic is showing, please ask me tomorrow. I'll explain it again. But what I want to ask you about are these 2 questions here at the bottom. How would this graph look differently for O2 or for N2? And then also, what about HH single bond, which are being shown in the graphic, versus an HF bond? Okay, as a hint, for this one here, the O2, N2, H2 issue, think about what type of bond might be holding them together. And then here, let's think about bond polarity a little bit, okay? So do me a favor. If you're kind of following me along here, pause the video and ponder this a moment. Think about it, and I'll come back and show you the answer. Okay, so hopefully you've had a chance to at least ponder it a little bit, to think about what is the difference in the bonds, whether it's how many bonds, or whether it's polarity of bonds, okay? So here's the full answer, okay? Just kind of read it along with me. I have a small version up here for you to kind of take a look at with the graphic. Okay, so the H2O2N2, they differ in the number of bonds. This is a single bond, this is a double bond, and this is a triple bond. So if they differ in number of bonds, it means their bond length and strength is different. So for O2, the bottom trough, which would be right here, of the graph, will have a bond length of less than 74 picometers because they will be held tighter together. So it'll be maybe somewhere like up in here, the bottom trough. And a bond energy will be more negative than the negative 432 kilojoules. And that's because it's stronger. Because remember, this delta H value, this enthalpy value that we're talking about, is representing strength. So it'll be more negative if it's a stronger bond. The N2 trough will follow the exact same trend. It's got a triple bond, so the trough will actually be up a little bit higher here with your values, and it will even have a more negative bond energy, okay? And so then here for the hydrogen-hydrogen single and the hydrogen-fluorine single, they differ in bond polarity, and then hence also the bond length and bond strength. So since the HF has a longer bond length, because basically the fluorine is pulling those electrons towards it, and it kind of pushes that hydrogen a little bit further away, it's going to have a longer bond length, and it's also going to have a higher bond energy. And then the hydrogen-hydrogen single, and that's all because of polarity. Okay, so this is just kind of a little extra added on thing. They tend to be focusing in AP right now on graphics and understanding of graphics. So again, this is something we can talk about tomorrow if you have questions. But this is it for the presentation today. So I hope you have a wonderful evening, or perhaps it's very, very early morning. I don't really know. But that's it for today. We'll see you later.